In this supplementary lecture, I'm going to talk about the Bloch sphere. Bloch sphere is a geometrical representation of quantum state of a two-level system or qubit states as points on the surface of a unit sphere. This representation is particularly useful for quantum information science. We learned in lecture 2 that any 2 by 2 matrix can be written or expressed in terms of the Pauli matrices sigma x, sigma y, and sigma z, and the identity matrix. And we know that the sigma x is equal to 0 1 1 0, sigma y is represented as 0 minus I 0, and sigma z is equal to 1 0 0 minus 1, and the identity matrix is 1 0 0 1. So any 2 by 2 matrix can be expressed in terms of this Pauli matrices and the identity matrix. So we have, say, this is my x direction, y direction, and z direction. So if I ask now, what about Pauli matrix along any arbitrary direction, say n cap, defined as n cap is equal to, say, sine theta cos phi, sine theta sine phi, and cos theta. So this is if this angle is, say, theta, and okay, let me just draw a little bit bigger picture here. So I have, this is my x-axis, this is y, and this is z. So any arbitrary direction, say eta cap, defined by this angle. So this is the theta angle. So I am sure all of you know I am just talking about spherical polar coordinate here. So this is the angle phi. Okay, so what about the Pauli matrix along this direction? Now you can take the q from this fact that sigma x, we can write it as the Pauli vector along x direction, x cap. Sigma y is the Pauli vector along y direction, and sigma z is equal to the Pauli vector along the z direction. So quite clearly now I can write the Pauli vector, Pauli matrix, the component of the Pauli matrix along, say, this arbitrary direction n cap would be sigma dot n cap, which I can now write as sigma x, and what is the component of n cap? So x component is this, y component is this, and z component is this one. So let me write all the components. So I will have sigma x sine theta cos phi, and then I will have sigma y sine theta sine phi, and I will have sigma z cos theta. Now I know the matrix form of sigma x, sigma y, and sigma z, so I can write the whole thing in a 2 by 2 matrix in this form. So I will have here cos theta because of this, and here I will have minus cos theta. Then because of sigma x and sigma y, I will have here sine theta cos phi minus I sine theta sine phi, and here I will have sine theta cos phi plus I sine theta sine phi. And of course this should be the case because this matrix is a Hermitian matrix. Now you can, if you have followed lecture 2, you can immediately work out the eigenvalues here. In fact, let me first write it, these Pauli matrices, in a little bit more compact form. I can write it as cos theta, and here it would be sine theta e to the power minus I phi. Okay, minus I phi is cos phi minus sine phi, I sine phi, and here I will have sine theta e to the power plus I phi, and here I have minus cos theta. Now you can immediately write down the eigenvalue of this Pauli matrix, And if you have followed lecture 2, you know how to calculate the eigenvalue immediately. So it would be simply plus minus square root of uh, cos square theta and modulus of this one. So this would be sine square theta, and therefore you will have plus minus 1. Now let us find out the eigenstates. Eigenstates corresponding to the eigenstate corresponding to lambda is equal to plus 1. So let us work it out. Our matrix is cos theta, sin theta. Let me first write down the eigenvalue equation. I have here sin theta e to the power I phi, and here I have minus cos theta. Let me assume that the eigenstate is represented by this column vector uv, and eigenvalue is plus 1, and the eigenstate is represented by this. From here I can immediately get this equation. I have u cos theta plus v sin theta e to the power minus I phi, and this is equal to u, which I can write again as u 1 minus, I'm taking it this side, okay, 1 minus cos theta, and I have here v sin theta e to the power minus I phi. Let me now write it as u twice sine square theta by 2, and here let me write it as v 2 sine theta by 2 cos theta by 2 e to the power minus I phi, and from here I write u sine theta by 2 is equal to v cos theta by 2 e to the power minus I phi. So therefore I can immediately guess u and v. Let me write u is equal to cos theta by 2, then I must have this v as e to the power plus I phi sine theta by 2, okay, and this I can express as cos theta by 2 1 0 plus e to the power I phi sine theta by 2 0 1. In fact, you know that this I can represent it as a kth vector or kth state, eigenkth 0, and this I can represent as 1. You can notice that this eigenvector corresponding to the Pauli vector along an arbitrary direction, which can be represented as a superposition of kth state 0 and kth state 1, is dependent on the angle theta and phi. So this actually led Felix Bloch came up with the idea that every point theta phi on the surface of a unit sphere could represent a unique state of a two-dimensional Hilbert space. An arbitrary single qubit state can be written as, say, kth psi is equal to cos theta by 2 kth 0 plus e to the power I phi sine theta by 2 kth 1. The range of the values for theta and phi are such that they cover the whole sphere without repetition, and theta will lie between 0 and pi. On the other hand, phi would it would be lie between 0 and 2 pi. Theta corresponds to the latitude and phi correspond to the longitude, as you may already know. So let me draw it once again. So we have this sphere which is now known as the Bloch sphere. So this is the equatorial plane. So let us say this is my x-axis, this is y, this is z, and a arbitrary point on the sphere is, say, this one, and this angle is theta, and this is the angle phi. To give you some example, let us say for theta is equal to 0 and phi is equal to 0, immediately from this expression you will see that would be equal to, this will represent the state k0, and as theta is equal to 0 and phi is equal to 0, this would mean this particular point. So let us say this is the north pole. So the north pole corresponds to the state k0 on the Bloch sphere. So north pole represents k0. Similarly, you can immediately actually see that for theta is equal to say pi and phi is equal to 0, then we'll have this k psi would represents k1, and this would be the south pole. On the other hand, if I now take say theta is equal to pi by 2 and phi is equal to 0, this will correspond to the point where the positive x-axis, so this is the positive x-axis, meets the equator. Let us say this is point A, and this point correspond to the state k psi is equal to, it's a superposition state, then you can immediately verify this will be 1 by root 2 k0 plus k1. So every point on the Bloch sphere represents a unique pure quantum state in the two-dimensional Hilbert space.